Hi guys, just hopping on here to finish up that Unit 3 lecture. So photoelectric effect, thing we've talked about before. If you can add enough energy to something, we're able to remove electrons from it. So this is like the principle behind ionization energy, binding energy, that kind of thing, that we've talked about before. I think like they don't ask about this usually, but I think it's an important distinction just for like people who know things about science. When we say this, it's super important that we realize that it's about the amount of energy the photon has. So, like, let's say a certain thing has a certain ionization energy. The photon, like a property of that photon, is that it has to have energy greater than the ionization energy. Enough energy in the photon to do that work. It's not about like how bright the light is or anything like that. It's about like that individual photon, how much energy does it have, what is like it's a property of the light. So I know that like seems a little bit weird. Like I've seen a lot of people like misconstrue it of like, oh well, if you just like make the light brighter, it like that feels right? Like if you make the light brighter, it should have more energy. It doesn't. Like let's say you had like a blue laser. The blue laser is, I'd have to double check, in the like 500 nanometers range. Like property of that light is that all of the blue light has that same nanometer, that same amount of energy. If I got a brighter laser, I just get more photons coming out of the laser at a given moment. The individual photons don't actually have more energy. So just to clarify that, again, that doesn't really come up for this class, but it's about the energy that the photon has. So maybe you're seeing some connections here. This is really just that we're trying to be able to assess and like be able to calculate what the binding energy of something is, or assess if a certain photon has enough energy to overcome binding energy, to overcome ionization energy. So since we know that energy is related to like wavelength and frequency, we could calculate this kind of thing based on any of those three properties. So yeah, just a concept like that. Let's take a look-see at this. It's back, PES. So here's a graph about the binding energy of some substance. And it's saying that we would need to figure out what the wavelength of light we would need in order to remove an electron from the valence. So reminder of how to read these. Over here, we got the 1s because it has the highest binding energy. And then we go down and there's a peak for each orbital. So 1s, 2s, 2p, 3s, 3p, 4s. So 4s right here, that is our valence electrons. And those valence electrons have a binding energy of, it's labeled for you, beautiful, that many joules. So the question is asking to calculate the wavelength of a particle, a photon, of a bit of electromagnetic radiation. All means the same thing. What would the wavelength of that energy be if it was able to meet this ionization energy, this binding energy, to overcome it? So all it's really asking is to change this energy into wavelength. Sick. We know an equation to do that. We know that energy is equal to h, frequency. And we know that that doesn't have wavelength in it. We also know that speed of light is equal to frequency times lambda, which is wavelength. So, different options. I recommend squishing these two equations together in order to be able to translate from energy to wavelength. I'll just show you like the steps of how I'm going to rearrange this stuff, just in case that feels a little weird to you. If you haven't like done much variable math before, you can just skip ahead if you're comfortable with this kind of math. So I want to, instead of having velocity here, I want to have wavelength instead, or something with wavelength in it. So going to rearrange this equation, divide my lambda over. Frequency is equal to the speed of light over lambda. And then I can just plug that in over here. So now I have the energy is equal to h over c lambda. Some people would then rewrite this as ch over lambda. So energy is equal to ch over lambda. Now, if you prefer, you could just plug in stuff here, plug in numbers at this point, and solve for lambda. That'll work. I like rearranging my equation first, just that way you don't like accidentally, like it'll be easier if you only have to like plug it into the calculator once, and like it just will be clearer what your calculation is instead of having to like rewrite all your numbers every time you try to solve for lambda. So I'm gonna do that. So to do that, I'll first multiply over my lambda. So multiply both sides by lambda. Energy times lambda is equal to hc. I want to get lambda alone, so then I'll divide back the energy. Lambda is equal to hc over energy. There we go. So that'll just make it easier instead of having to do that. Again, if you prefer to do it in multiple steps because like working with just variables is confusing, that's fine too. Whatever. But now I have this equation. H is a constant. Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Oh, I ran out of room. That's fine. Times the speed of light, which is 2.998 times 10 to the 8th meters per second. And the energy that this photon, this bit of radiation would need is this much energy, that many joules. So 0.980 times 10 to the negative 18 joules. Now, big units guy, big fan. I put my units in the math because that way I'm sure that I have the right units. Because, like, what if your energy was given in kilojoules and you didn't realize that these units wouldn't talk to each other? So I just think it's helpful to always do that. It's okay if you don't quite see this, but the seconds are going to cancel here, the joules cancel here, and so this equation right now, as it's set up, is solving for meters, a wavelength in meters. Pause and actually plug this into your calculator. Make sure you actually are able to do it and get the right answer. Sometimes scientific notation can be weird in calculators. Make sure it's actually working for you. What you should have gotten is that lambda, our wavelength, is equal to 2.02 times 10 to the negative 7 meters. Ba-boom. I know the question just asked for meters, but it's super common for wavelength to be in nanometers. So I just want to point out like how you would do that if you were asked to. So this is something that you just kind of got to memorize. This is one of those key metric conversions that comes up all the time. If you get a little n in front of your base unit, it means that there are, and you can write it either way, whichever makes sense for you. There are 10 to the 9th nanometers in 1 meter. Same thing as saying that there's 1 nanometer and 10 to the negative 9 meters. I don't mean to confuse you by saying both. Whichever works better for you, just remember one. Nanometers are smaller than meters. So if you accidentally mess up this ratio, that's okay. You'll just realize that, hey, my number didn't get smaller. Or I'll show you in a sec. But like if I measure something that's 100 centimeters, and then I translate that to meters, it's like a very small fraction of a meter, right? So same principle. If we're going from a meter to a nanometer, the unit should translate the correct way. So if you don't see the like change you would expect, like nanometers usually are like in the hundreds with no times 10 to the anything. So if you don't get that, like you probably put it up like the wrong side. But just let me show you this. So if you were asked for nanometers, you would just use that conversion factor. I like dimensional analysis, so that's what I'm going to do. So write my answer we already calculated, 2.02 times 10 to the -7 meters. And I want to cancel out my meters and change it into nanometers. There are 10 to the 9 nanometers in 1 meter. Ooh. Meters cancel out. Left with nanometers, and that answer would now be 202 nanometers, which is, in my opinion, a much easier number to look at. So, very common. Again, usually nanometers, like, if you're talking about like photons, it's going to be like 100 in the hundreds. Like, it's going to be a nice number like this without a big scientific notation. If it's times 10 to the -20, you went the wrong way, you flipped this fraction the wrong way. Sick. Oh yeah. Okay, so that's kind of it for photoelectric effect. It's mostly always questions just like asking you to calculate energy or calculate wavelength or whatever. Our final topic is Beer's law. I didn't type up a skeleton note for you for this. I'm sorry, but there's a blank page on the back. I believe that you can handle writing a little bit more. It'll be okay. So our final topic is 3.13, Beer's law. So this is what we're going to do our lab on Tuesday. So we'll go over this a lot more. You'll see the like actual lab techniques and how we actually use this. So like don't stress too much about it. I just wanted to give you a overview first. So this is a common thing we do when using photospectroscopy, that type of spectroscopy I talked about earlier today, the kind where we shoot radiation at something, energy at a sample, and see what gets absorbed by it, what types of energy, what wavelengths of energy get absorbed. So here's how, let's take a zoom on in. What does it look like inside a photospectrometer? How does this experiment usually work? So just a little simple, just to give you an idea of how this goes, you have some kind of lamp, something with light coming out of it. And that lamp is going to be it's a full light bulb, which has the whole visible range. If it's a fancy one, then it also has UV. I'm pretty sure we only have visible. The super fancy ones can do even more, but most of the time it's a lamp that's just doing visible range. And that is being shot, and all of those photons of all those different wavelengths are coming off of it, and they're going towards our sample. The sample is in a little square thing like this inside of the spectrophotometer. The name for this is a cuvette, because it's a cube. It's not really. So you fill this up like 3/4 up, and in there you have your solution of whatever sample you're trying to measure. And this sample will absorb some of the light. So some of it will get absorbed and interact in a certain way with our solution, depending on its characteristics, depending on what light it absorbs. But some of it will keep passing through. And then on the other side of the machine, there's a detector. And so this detector's job is to read it's to read how much light passes through, but the way it's going to report that is reading which wavelengths of light got transmitted. So it's actually reading what light is getting to the detector. That's what's actually reading. But from that, any light that it's reading, source, what it's reading, the difference is whatever got absorbed, right? So this, it usually, you can get it to report what was transmitted, but that's not as helpful. So it'll just read it out to you as tells you which were absorbed. absorbed. And I just absorbed abs. And you can tell how much. Like relatively. So this is, we'll get, like if you wanted to graph this, you would get some kind of graph like this. I mentioned this earlier, any photospectrometer would give you some sort of this. You got bumps, and these wavelengths refer to wavelengths of light that actually get absorbed by your sample. Again, we'll talk more about that with the lab, but you get some kind of reading, and we'd tell, okay, some of the light got absorbed, cool. So what the heck is Beer's law? Beer's law is one of the ways we deal with this data. Beer's law just tells us that the amount of energy that gets absorbed, like the intensity, like how many of those photons are actually getting absorbed by the sample, is related to the concentration of the sample. So that's all it is. And we have a simple, cool equation to help us with that. A is equal to epsilon BC. A is absorbance. So that is just like a number that tells me, okay, how much of the light at that wavelength got absorbed. Again, I'll show the experimental setup with the actual lab. There are no units on absorbance, which is strange, but it is true. B is the path length. All that means is how big was your cuvette? How far did the light have to travel through the cuvette? Just basically showing like how much of the substance did it have to travel through. But ingeniously, we made all the cuvettes 1 centimeter. So that's a 1 in the equation. You can usually ignore it. Like, if it was an FRQ, you'd write your full equation, but it's 1. So not going to affect our number. Cool. Concentration. Of the sample, of the solution. Usually molar, but you'd look at your graph and double check that it's in molar. It'd be whatever you made your solution to be. And then this is the molar absorptivity. Cool. You don't need to stress too much about that. This is a property of the substance. So they'd either have to give it to you or give you like a graph or some data where you could determine it experimentally. It's a property of the substance. So like, let's say I have a certain molecule, let's say like a dye. This is super common with like a colored substance, like a dye or a colored solution. Let's say that specific dye, I guess we don't think about that much, but like the reason a dye is a certain color is because the dye molecules are a certain shape, and so that certain shape with certain bonds absorbs certain lights, and color is from absorbing lights, which I know hurts the brain a little bit. We don't need to think about it that much. But the way that molecule is structured defines how it's going to interact with light. So even if I have only like a few of those molecules versus a whole very concentrated solution, they're all going to interact with light in the same way. They're going to have the same molar absorptivity. So don't need to stress too much about that. So again, usually the units on the concentration are molar. If they are, then the units on this one are like inverse, like 1 over molar centimeters. You pretty much never have to like actually solve that. But it's just whatever the units on this would depend on the units of this. They all cancel out because this has no units. Again, we'll actually do a thing with it later. You don't need to stress too much about that. So we'll actually do this later, but just to give you a kind of idea of like, what the heck will we do with this? So when I want to use Beer's law, I usually want to like figure out the concentration of something using its absorbance. So being able to pop a little sample in a spectrophotometer and figure out how much light was absorbed, therefore giving me the concentration, because they have these direct relationship. So what you would do is you're going to make a bunch of solutions of known concentration. So using those molarity calculations that we've now learned, you could know how much to weigh out of each thing, or make dilutions of a stock solution, which is what we're going to do. Then you would want to measure the absorbance of each. And you'd plot it, and you know, this is just an example, just to give you the idea. You don't have to make it look good, but absorbance, and then you'd have all your different concentrations on your X. Then you get some dots, and hopefully the dots will be in a fairly straight line. And then you'd make a line through all the dots, a trend line, a line of best fit. You are graphing absorbance as your Y and concentration as your X. If C is the X and A is the Y, and they're in this relationship together, and I didn't draw it that well, but it should start ideally at the origin, so it starts from 0 x-intercept, y-intercept, I'm sorry, been a second. That means that this part is your slope. Again, B is 1, so your slope is your molar absorptivity. So you could experimentally determine the molar absorptivity of something, or you could measure the absorbance of a sample, plug it into your line of best fit equation, and find X, find your concentration. So that's what we'll actually practice doing next week. But hopefully this gives you a little bit of an intro to it. And yeah, I think that's it. Email me if you have any questions, and have a great weekend. Okay, actually no.